Welcome back to The Explainer. Today, we're tearing into Chapter 4, the atmosphere. Now look, we're not just going to treat this like some boring, static layer of gas floating above our heads. Oh no, absolutely not. I want you to picture the atmosphere as this massive, dynamic, interconnected thermal engine. It's literally driving our planet's weather, the climate, basically our entire habitability. We're going to break down exactly how this giant engine is built, how it's fueled by the sun, the moving gears of pressure and wind, and finally, its exhaust system of clouds and precipitation. Let's get right into it.
All right, so here's our roadmap for today. We're covering the structure of the atmosphere, insulation and the heat budget, atmospheric pressure and winds, air masses and cyclones, water in the atmosphere, and we'll wrap it all up by solving some UPSC prelims previous year questions.
Section 1. Structure of the atmosphere.
The atmosphere is a complex mixture of different gases, water vapor, and dust particles that envelopes the Earth from all sides. About 99% of its total mass is concentrated within just 32 kilometers of Earth's surface. It is essential for life, providing oxygen for respiration and carbon dioxide for photosynthesis, while also acting as a thermal blanket that keeps Earth warm enough for life to exist. Composition of the atmosphere. Atmospheric gases. Nitrogen 78%. Inert gas. Essential for plant growth. Most abundant gas in the atmosphere. Oxygen 21%. Supports combustion and respiration. Key fact, marine phytoplankton and photosynthetic bacteria produce about 50% of world's oxygen. Important, well-oxygenated surface water contains far less oxygen than atmospheric air, not more. This is a common UPSC trap. Argon 0.93%. Inert gas. No significant role. Carbon dioxide 0.03 to 0.04%. Used in photosynthesis. It is a greenhouse gas, transparent to incoming short-wave solar radiation but absorbs outgoing long-wave terrestrial radiation, trapping radiation and heat, maintaining Earth's average temperature. Ozone. Found between 10 and 50 kilometers above Earth's surface. Absorbs solar ultraviolet rays, protecting life on Earth. Water vapor. Most variable component of the atmosphere. Varies from 0% in cold, dry polar or desert air to 4% in warm, wet tropics. Concentrated in the lower atmosphere. Primary absorber of near-infrared radiation. Key properties. Decreases with altitude and from equator towards poles. Acts like a blanket, allowing the Earth neither to become too cold nor too hot. Dust particles. Microscopic solids that help in condensation and scatter light. Highest concentration in subtropical and temperate regions due to dry winds, arid conditions, sparse vegetation, and stable air in high-pressure belts. Equatorial regions, high humidity and rainfall washes out dust. Polar regions, ice and snow cover prevents dust generation. Structure of the atmosphere. The atmosphere is divided into 5 distinct layers based on temperature trends. Let's go through each one carefully. Layer 1, Troposphere. Height, average 13 kilometers, 8 kilometers at poles, 18 kilometers at equator. Temperature trend decreases with height at the normal lapse rate of 6.5 degrees Celsius per kilometer. Key characteristics. Thickness is greatest at the equator because heat is transported to great heights by strong convectional currents. Contains dust and water vapor. All weather phenomena occur here: rain, clouds, storms, cyclones. Tropopause, boundary with stratosphere, temperature is constant at -80 degrees Celsius over equator and -45 degrees Celsius over poles. Layer 2, Stratosphere. Height up to 50 kilometers. Temperature trend increases with height because the ozone layer absorbs UV rays and releases heat. Key characteristics. Contains the ozone layer which absorbs UV rays. Almost free from clouds and weather, ideal for flying jet aircraft. Stratopause marks boundary with Mesosphere. Layer 3, Mesosphere. Height up to 80 kilometers. Temperature trend decreases with height, coldest layer, reaching -100 degrees Celsius. Key characteristics. Meteors burn up in this layer upon entering from space. Noctilucent clouds, highest clouds on Earth, form here. Mesopause marks boundary with Thermosphere. Layer 4, Thermosphere, Ionosphere. Height 80 to 400 kilometers. Temperature trend increases rapidly with height up to 1200 degrees Celsius. Key characteristics. Contains electrically charged particles called ions. Reflects radio waves back to Earth, enables wireless communication. Site of auroras, Aurora Borealis in Northern Hemisphere and Aurora Australis in Southern Hemisphere. Home to many satellites. Layer 5, Exosphere. Height above 400 kilometers. Temperature very high. Key characteristics. Outermost layer. Extremely rarefied gases. Gradually merges with outer space.
Section 2, Insulation and Heat Budget. All right, so
Atmospheric thermodynamics, insulation and heat budget. Atmospheric thermodynamics involves the study of heat exchange between the sun, the earth, and the atmosphere, which determines weather patterns and global climate. The earth maintains a constant temperature by ensuring the energy it receives, called insolation, is balanced by the energy it emits, called terrestrial radiation. This balance is called the heat budget. Incoming solar radiation, insolation. Nature, received primarily in short wavelengths, 0.39 to 0.76 micrometers. Factors influencing insolation. Rotation of Earth causes day and night, determines how long a place receives sunlight. Angle of sun's rays, slanting rays at higher latitudes spread over a larger area, less intensity, more atmospheric absorption. Vertical rays at lower latitudes, more intense. Length of day, longer daylight, more insolation. Atmospheric transparency, clouds, water vapor, dust reflect, absorb, scatter radiation. Subtropical deserts receive maximum insolation due to clear skies. Configuration of land, south-facing slopes in northern hemisphere receive more sunlight than north-facing slopes. Land heats and cools faster than water due to its lower specific heat capacity. Sunspot, increase in sunspots, increase in insolation. Latitudinal and spatial distribution. Equator receives approximately 5 times more insolation than polar regions, not 10 times. Remember this, it was a UPSC trap question. Equator actually receives less insolation than tropics because of cloud cover and high humidity. Subtropical deserts receive highest insolation, minimal cloud cover. Same latitude, insolation is higher over continents than oceans. Winter season, middle and higher latitudes receive less insolation. Temporal variation. Insolation is higher on 3rd January, perihelion, when Earth is closest to Sun, than on 4th July, aphelion, when Earth is farthest. Albedo. Definition, proportion of solar radiation reflected back to space without heating the surface. Key fact, atmosphere is transparent to incoming shortwave radiation but opaque to outgoing longwave radiation. Earth's albedo, approximately 30 to 35 units of incoming radiation, is reflected back. Cloud impact. Low, thick clouds, stratus type, have high albedo cooling effect. High, thin clouds, cirrus type, transmit incoming radiation but trap outgoing infrared heat warming effect. Order of albedo from highest to lowest. Fresh snow, ocean ice, sand, green grass, forest, open ocean, charcoal. Heating and cooling of atmosphere. Keynote, the atmosphere is heated mainly by outgoing long-wave terrestrial radiation compared to incoming short-wave solar radiation. 4 mechanisms. Conduction, heat transfer by direct contact between warm land and cooler air. Heats the lower atmosphere. Convection, vertical heat transfer. Warm air rises, expands, and spreads heat. Confined to troposphere. Advection, horizontal heat transfer by air movement. More significant in middle latitudes. Causes low in North India and daily weather changes. Terrestrial radiation. Primary heating source of atmosphere. Long-wave terrestrial radiation from the ground is more important than incoming solar radiation. Greenhouse gases like CO absorb long-wave infrared radiation. Without atmosphere's ability to trap heat, Earth's surface temperature would remain well below the freezing point everywhere. Heat budget. Of 100 units of incoming solar radiation, 30 units are reflected back to space, 6 by atmosphere, 17 by clouds, 7 by surface. 23 units are absorbed by air, water vapor, ozone, clouds, dust. 47 units are absorbed by ocean and land. From the 47 units absorbed by Earth's surface, 7 units transferred by conduction. 24 units transferred as latent heat. 10 units radiated as long-wave radiation absorbed by water vapor, ozone, CO. Remaining radiated upward, 40 units radiated from HO, ozone, CO, 20 units radiated from clouds. Net result, Earth maintains equilibrium. Energy in equals energy out. Heat budget imbalance and human stress. Radiative forcing. Change in net downward radiative flux at top of atmosphere from factors altering energy balance. Refers to the difference between energy entering and leaving Earth's atmosphere, called so because the difference in energy can force changes in Earth's climate. No forcing, incoming and outgoing radiation balanced. Positive forcing, Earth gains energy warming caused by GHGs like CO and black carbon. Negative forcing, Earth loses energy cooling caused by aerosols and volcanoes. Used to compare the influence of different drivers on climate change. IPCC uses 1750 as baseline year. Wet bulb temperature. Lowest temperature achievable by water evaporation on a thermometer evaporative cooling limit around 25 to 28 degrees Celsius in dry heat. Human lethality threshold. Sustained 31 to 35 degrees Celsius wet bulb temperature, 87 to 95 degrees Fahrenheit, as sweat fails at high humidity. Core body above 37 degrees Celsius is fatal even for healthy individuals. Combines air temperature and humidity to indicate the lowest temperature air can reach through evaporation of water. At critical threshold of 35 degrees Celsius wet bulb temperature, sweat cannot evaporate effectively for healthy individuals and animals. The World Bank warned that India could become one of the first places where wet bulb temperatures routinely exceed 35 degrees Celsius. Heat index, apparent temperature. Combines air temperature and relative humidity for the feels like heat in shade. Thresholds, caution 27, 32 degrees C, danger 39, 51 degrees C, extreme above 52 degrees Celsius, hyperthermia risk. Universal Thermal Climate Index. Equivalent temperature factoring air temperature, humidity, wind, radiant heat, clothing, and activity. Temperature. The interaction of insolation with the atmosphere and the Earth's surface creates heat, which is measured in terms of temperature, the measurement in degrees of how hot or cold a thing or a place is. Factors controlling temperature distribution. Latitude, higher latitude, lower temperature, less direct sunlight. Altitude, higher altitude, lower temperature, at 6.5 degrees Celsius per kilometer normal lapse rate. Distance from sea, coastal moderate temperature, interior extreme temperature, continentality. Ocean currents, warm currents raise temperature of coastal areas, cold currents lower temperature. Cloud cover, clouds reduce daytime heating by reflecting sunlight, increase night temperature by trapping outgoing radiation. Slope, sheltered slopes receive less wind, sunny slopes receive more insolation, local temperature variation. Vertical distribution of temperature. Normal lapse rate, temperature decreases with height at 6.5 degrees Celsius per kilometer. Temperature inversion. A reversal where temperature increases with altitude opposite of normal. Conditions for temperature inversion. Long winter nights, clear skies, still air, and dry air. Temperature inversion is normal throughout the year in polar regions. Types. Surface inversion, by conduction, surface loses heat rapidly on clear nights. Valley inversion, air drainage and katabatic winds, cold dense air drains into valleys. Frontal inversion, warm air overriding cold air at a front. Horizontal distribution of temperature. Normal lapse rate, temperature decreases with height at 6.5 degrees Celsius per kilometer. Temperature inversion. A reversal where temperature increases with altitude opposite of normal. Conditions for temperature inversion. Long winter nights, clear skies, still air, and dry air. Temperature inversion is normal throughout the year in polar regions. Types. Surface inversion, by conduction, surface loses heat rapidly on clear nights. Valley inversion, air drainage and katabatic winds, cold dense air drains into valleys. Frontal inversion, warm air overriding cold air at a front. Horizontal distribution isotherms. Isotherms, lines joining places with equal temperature, generally parallel to latitudes. Land-water contrast. Specific heat of water is greater than land, land heats and cools faster than the ocean. Isotherms are irregular and closely spaced in northern hemisphere due to more land-water contact. Isotherms are regular and widely spaced in southern hemisphere dominated by oceans. January, winter in northern hemisphere. Isotherms bend equatorward over land, land is colder. Isotherms bend poleward over oceans, oceans are warmer, aided by warm currents like Gulf Stream. July, summer in northern hemisphere. Isotherms bend poleward over land, land is warmer. Isotherms bend equatorward over oceans, oceans are cooler. Key contrast. Winter, land loses heat quickly, very cold, ocean stays warmer, high contrast. Summer, land heats up quickly, oceans also warm, somewhat lesser contrast. Therefore, temperature contrast between continents and oceans is greater during winter than in summer. Temperature anomaly, the difference between a place's temperature and the mean temperature of its latitude.
Okay, moving on to Section 3, Atmospheric Pressure and Winds. We've got our heat budget set, so let's look at the moving gears of this atmospheric engine.
Atmospheric circulation and weather systems. Atmospheric circulation is the large-scale movement of air that redistributes heat and moisture across the planet to maintain a constant global temperature. This motion is driven by variations in atmospheric heating, the emergence of pressure belts, and the rotation of the Earth. Atmospheric pressure. Definition: the weight of a column of air contained in a unit area from mean sea level to the top of the atmosphere. Pressure is uneven, varies vertically and horizontally. Lower layers have higher density, higher pressure. Vertical variation decreases with altitude. Not uniform, depends on temperature, water vapor, gravity. Vertical pressure gradient is greater than horizontal pressure gradient. Rising pressure stable weather, falling pressure cloudy and unstable weather. Horizontal variation, shown by isobars, lines of equal pressure. Closely spaced isobars, steep pressure gradient, strong winds. Instruments, measured using a mercury barometer or aneroid barometer. Forces governing wind. Wind is the horizontal movement of air from high pressure to low pressure areas. Pressure gradient force, PGF, moves air from high to low pressure. Strength indicated by spacing of isobars. Coriolis force, CF, deflects winds to the right in northern hemisphere and to the left in southern hemisphere, Ferrel's law. Absent at the equator, preventing cyclone formation there. Maximum at the poles. Acts perpendicular to PGF, deflection increases with higher wind velocity. Centripetal force, acts perpendicular to the wind, converging inward. Frictional force, affects wind speed in lower atmosphere. Minimal over sea surfaces. Geostrophic winds, located in upper atmosphere, 2 to 3 kilometers above surface, free from friction. When PGF is balanced by Coriolis force, wind blows parallel to isobars called geostrophic winds. Global pressure belts and atmospheric cells. The horizontal distribution of pressure follows a latitudinal pattern of alternating high and low belts. 1. Equatorial low, doldrums, 5 degree N to 5 degree S, thermal origin. Zone of intense heating and low pressure. Doldrums, zone of ITCZ, intertropical convergence zone, convergence of trade winds, leads to heavy convectional rainfall. 2. Subtropical high, horse latitudes, tilde 30 degree N and S, dynamic origin. Formed by subsidence, sinking of air from the Hadley cell. Known as horse latitudes. Associated with clear skies and deserts due to sinking air preventing cloud formation. Example, Sahara, Arabian desert. 3. Subpolar low, tilde 60 degree N and S, dynamic origin. Convergence of westerlies and polar easterlies. Site of polar fronts and cyclonic storms. 4. Polar high, 80 degrees to 90 degree N and S, thermal origin. Extremely low temperatures cause air compression and increased density. High pressure due to cold, dense air. Atmospheric cells, TRI cellular model. Hadley cell, rising air at ITCZ sinks at subtropical highs around 30 degrees. Completes the loop as surface trade winds blowing from 30 degrees toward equator. Ferrel cell, sinking air at 30 degrees and rising air at 60 degrees. Characterized at the surface by westerlies blowing from 30 degrees to 60 degrees. Polar cell, subsiding air at poles moves toward mid-latitudes as polar easterlies. Rises near 60 degrees. Planetary winds. Planetary winds, also called permanent or prevailing winds, constitute the large-scale general circulation of the atmosphere. They blow consistently in the same direction throughout the year, redistributing heat from lower to higher latitudes. 1. Trade winds, tropical easterlies, blow generally from east to west from subtropical high at 30 degrees to equatorial low at ITCZ. Characteristics, most consistent in force and direction. ITCZ, intertropical convergence zone, 0 degrees to 10 degree S, to trade winds meet at the equator. Intense heat causes ocean water to evaporate. Rising air, clouds, heavy rainfall known as thermal equator forces moist air to rise. Calm, windless equatorial ocean belt, doldrums, convection, clouds, heavy rain. Onshore on eastern coast of continents, trade winds bring moisture and heavy rainfall. Offshore on western coasts, leads to dry conditions and deserts on the western coasts of continents. Examples, Sahara, Atacama, Kalahari. Climatic impact, heavy rain on eastern tropical coasts, dry toward western margins, trade wind, deserts. Oceanic effect, push warm water westward. Western tropical oceans are warmer than eastern. Climate change, ITCZ shift may alter rainfall belts, risk to Amazon and Congo carbon sinks. 2. Westerlies, blow generally from west to east from subtropical high at 30 degrees toward subpolar low at 60 degrees. Stronger in southern hemisphere due to less land resistance and water predominance. Names, roaring 40s at 40 degree S, furious 50s at 50 degree S, screaming 60s at 60 degree S. Weather impact, westerlies make the eastern sections of oceans warmer than western sections. India link, responsible for bringing rain-bearing western disturbances to northwestern India during winter. Western disturbances, moist air masses, bring winter rainfall in NW India, crucial for Rabi crops. Climate change, poleward shift reduced winter rainfall in Mediterranean climates, Cape Town crisis. 3. Polar easterlies, cold, dense air subsiding at polar high pressure belts blows toward subpolar lows. As this cold air moves toward 60 degrees latitude, it converges with the warmer westerlies, forming the polar front formation of temperate extratropical cyclones in mid-latitudes. Jet streams. Fast, narrow, meandering air currents in the upper troposphere and lower stratosphere above 9 to 13 kilometers altitude. Speed, 400 to 500 kilometers per hour. Seasonality, shift with the sun, poleward in summer and equatorward in winter. Major types. Subtropical jet stream, STJ constant in southern hemisphere. Influences the Indian monsoon onset when it withdraws from the Himalayas. Polar front jet, PFJ more variable and stronger in winter. Tropical easterly jet, TACE temporary summer jet. Steers tropic. Depressions into India. Rossby waves, pronounced wave-like patterns, meanders, developed by jet streams due to the conservation of angular momentum and temperature disparities. Climate change impact, as the Arctic warms faster, Arctic amplification, the temperature gradient with the tropics weakens, causing jet streams to slow down and meander more, leading to persistent heat waves or deep cold spells. Polar vortex. A large, persistent area of low pressure and extremely cold air surrounding both of Earth's poles. Features. Rotation, counterclockwise flow of air in the northern hemisphere contains the coldest air near the poles by the polar front jet stream in the upper atmosphere. Seasonal behavior, weakens during summer and strengthens significantly in winter. Vortex disruption, in winter, as the vortex expands, the polar front jet stream may shift equatorward or develop large undulations, Rossby waves. A weakened jet stream allows a portion of the vortex to split or dip southward, polar outbreak, bringing Arctic air into mid-latitudes of United States and Canada. Ozone connection, a strong, stable vortex can trap cold air, favoring the formation of polar stratospheric clouds, PSCs, which provide surfaces for chemical reactions that accelerate ozone depletion. Local winds. Local winds are regional air movements confined to the lowest levels of the troposphere, produced by localized differences in temperature and pressure. Warm and hot local winds. Lu, hot, dry summer wind over North India and Pakistan. Due to strong heating advection. Chinook, warm downslope wind on eastern Rockies. Called snow eater, melts snow. Foyhan, warm, dry wind on leeward side of Alps. Melts snow and helps grape ripening. Sirocco, hot, dusty Sahara wind toward southern Europe. Moist and red dust called blood rain. Also called Khamsin in Egypt, Ghibli in Libya, Chili in Tunisia, Leveche in Spain. Harmattan, dry wind from interior Africa to Guinea coast. Red. Reduces humidity. Called the doctor. Berg, hot, dry wind in South Africa, sometimes followed by rainfall. Cold local winds. Mistral, cold, dry, strong wind through Rhône Valley, France. Bora, cold, dry northeast wind toward Adriatic Sea. Pampero, cold west-southwest wind in Argentina and Uruguay. Buran, violent cold wind in Central Asia and Russia. Southerly burster, cold wind in Southeast Australia. Periodic local winds, diurnal. Land and sea breezes, due to differential heating of land and water. Sea breeze, day cool air blows from sea to land. Land heats faster, creates low pressure over land. Land breeze, night air blows from land to sea. Land cools faster, creates high pressure over land. Mountain and valley winds. Valley breeze, anabatic, during the day, warm air rises up mountain slopes from the valley. Mountain wind, katabatic, at night, dense cold air descends from slopes into the valley due to gravity. This air drainage can cause valley inversions, protecting or damaging plants depending on frost intensity.
Section 4. Air masses and cyclones.
AIR masses, fronts and cyclones. AIR masses. Definition, large body of air with uniform temperature and humidity over a vast area. Source regions, areas where air remains stationary for several days to acquire local characteristics, vast ocean surfaces or level plains. Keynote, mid-latitudes are not major source regions due to frequent cyclonic disturbances. Types. Air mass colder than underlying surface, cold air mass. Air mass warmer than underlying surface, warm air mass. Geographical classification. Maritime tropical, metricton warm, humid, source, over tropical oceans. Continental tropical, CT hot, dry, source, over subtropical deserts. Maritime polar, MP cool, moist, source, over high latitude oceans. Continental polar, CP cold, dry, frigid, source, over snow-covered high latitude continents. Continental Arctic, CA extremely cold and dry, source, over Arctic and Antarctica ice sheets. Fronts and frontogenesis. Front, boundary between two converging air masses with different temperature, humidity, and density. Frontogenesis, the process of formation of a front occurs mainly in middle and higher latitudes, 40 degrees to 65 degrees. Frontolysis, the dissipation or weakening of a front. Types of fronts. Cold front, advancing cold air violently displaces warm air upward. Characteristics, steep slope, cumulonimbus clouds, heavy rainfall and thunderstorms. Warm front, advancing warm air glides over a receding cold air mass. Characteristics, gentle slope, moderate and gentle precipitation over a large area. Stationary front, air masses are not moving against each other. Winds blow parallel to the front. Occluded front, when a cold air mass overtakes a warm air mass, lifting the warm air entirely off the ground. Cyclones and anticyclones. Cyclones, low-pressure systems. Air converges at low pressure in the center at the surface and rises upward leading to cloud formation and precipitation. Wind direction, anticlockwise in northern hemisphere, clockwise in southern hemisphere. Anticyclones, high-pressure systems. Air subsides from above and diverges at the surface at the high-pressure center leading to stable, fair weather. Wind direction, clockwise in NH, anticlockwise inch. Tropical cyclones versus temperate cyclones. Tropical cyclones. What violent storms that originate over oceans in tropical areas bring very heavy rainfall, storm surges, and widespread destruction in coastal areas. Also known as cyclone in Indian Ocean, hurricane in Atlantic, typhoon in West Pacific, willy-willies in Australia. Conditions of formation. Sea surface temperature greater than or equal to 26-27 degrees C up to tilde 60 m depth. Presence of Coriolis force. Small variations in vertical wind speed. Pre-existing low-pressure disturbance. Upper divergence above the sea level system. In South Atlantic and Southeastern Pacific, tropical cyclones do not originate because ITCZ seldom occurs there. Latitude 10 degrees to 30 degrees NS, rare near equator due to weak Coriolis force. Movement east to west under influence of trade winds. Nature and origin, thermal origin, over intense low pressure over warm oceans with no fronts. Latent heat of condensation from warm moist air provides energy. Temperate extratropical cyclones. What large-scale systems developing along the polar front in mid and high latitudes. Also called extratropical or mid-latitude cyclones. Conditions of formation. Strong temperature contrast between air masses. Formation along polar front. Upper air divergence. Instability due to frontogenesis. Latitude 35 degrees to 65 degrees NS more pronounced in northern hemisphere. Movement west to east under influence of westerlies. Nature and origin, dynamic origin, formed by frontal interaction of warm and cold air masses. Horizontal temperature contrast between air masses provides energy. Features. Smaller size, 100 to 500 kilometers in diameter. Steeper pressure gradient circular isobars. Very high wind speeds, 100 to 250 kilometers per hour. Short life, less than 1 week. Eye present at center, warmer than adjoining areas, in mature and intense tropical cyclones, not all cyclones. Torrential rainfall due to mostly cumulonimbus clouds. Relationship with jet streams is less clear. Affects East Coast, Bay of Bengal more than West Coast. Features. Larger size, 300 to 2000 kilometers in diameter. Lower pressure gradient V-shaped isobars. Moderate wind speeds, 30 to 150 kilometers per hour. Longer life, 2 to 3 weeks. No eye. Steady, widespread rain with multiple frontal cloud types. Strongly influenced by jet streams and Rossby waves. Brings winter rains, locally called Mahavat, to northwest India as western cyclonic disturbances crucial for rabi crops. Extreme weather and special events. Thunderstorms, caused by intense convection, associated with cumulonimbus clouds, lightning and thunder. Lightning, cloud updrafts collide ice and Groppel collisions transfer. Electrons charge separation, negative base, positive top builds electric field when breakdown voltage around 3 MVM is exceeded, invisible negative scout zap creeps down to meet ground's positive spark bright flash at 30,000 degrees Celsius heat. Thunder, flash superheats air explodes outward as shockwave rumbles, count 3 seconds per kilometer for distance. Twin cyclones, two cyclones forming on either side of the equator, longitudinally similar but in opposite hemispheres. Caused by equatorial Rossby waves. Rotate in opposite directions. Fujiwara effect, interaction between two tropical storms within 1,400 kilometers, can lead to merging or track alteration. Bomb cyclone, rapidly intensifying mid-latitude storm. Atmospheric pressure drops by at least 24 millibars within 24 hours, explosive cyclogenesis. Brown ocean effect occurs when cyclones intensify or sustain over land due to heat and moisture released from hot, waterlogged soils. Example, Cyclone Asna 2024.
Moving to Section 5, Water in the Atmosphere. Let's transition.
Water in the atmosphere. Water exists in the atmosphere in 3 states, gaseous as water vapor, liquid, and solid as ice. Its continuous circulation between oceans, atmosphere, and land driven by solar energy is known as the hydrological cycle. While water vapor accounts for only 0 to 4% of atmospheric volume, it is the primary driver of all weather phenomena. Core processes: evaporation, transformation of water from liquid to gas. Latent heat of vaporization, energy required to convert liquid into vapor at a constant temperature. Drivers: higher temperatures increase the air's moisture retention capacity. Air movement: wind replaces saturated layers with unsaturated air, accelerating the process. Condensation, transformation of water vapor into liquid caused by heat loss. Conditions: occurs when temperature reaches the dew point, saturation temperature, air volume is reduced, or moisture is added through evaporation. Condensation and hygroscopic nuclei, microscopic particles, dust, smoke, sea salt, pollen that provide surfaces for vapor to collect. Artificial rain, cloud seeding, based on adding hygroscopic condensation nuclei like salt or silver iodide to unsaturated air to trigger the condensation process. Forms of condensation: dew, water droplets deposited on cool solid surfaces, stones, grass, when dew point is above freezing point. Favorable conditions: clear sky, calm air, high relative humidity, cold and long nights. Clouds reflect back Earth's radiation, less cooling, no dew formation, that's why dewdrops are not formed on a cloudy night. Frost, minute ice crystals formed when the dew point is at or below freezing point. Fog, a mini cloud with its base at or near the ground, reducing visibility to less than 1 kilometer. Mist, similar to fog but contains more moisture. Each nucleus is surrounded by a thicker layer of moisture. Visibility is typically more than 1 kilometer. Smog, combination of smoke and fog. Classical smog, cold, humid climates, storage. Photochemical smog, sunny climates, due to nitrogen oxides and VOCs. Clouds. Clouds are masses of water droplets or ice crystals formed in free air at significant altitudes. Noctilucent clouds, 80 to 90 kilometers, Mesosphere. Earth's highest clouds, visible only at night when illuminated by sunlight from below the horizon. Polar stratospheric clouds, PSCs, 15 to 25 kilometers, winter stratosphere. Beautiful iridescent mother-of-pearl clouds. Provide surfaces for chemical reactions that accelerate ozone depletion. Cirrus, high altitude, 8 to 12 kilometers. Thin, white, feathery clouds composed of ice crystals. High, thin, transmit incoming radiation but trap outgoing heat warming effect. Cumulonimbus, vertical development cloud. Heavily developed vertical clouds with an anvil head. Associated with thunderstorms, lightning, and heavy rain. Cumulus, 4 to 7 kilometers. Cotton wool appearance with a flat base. Exist in patches. Stratus, low altitude. Layered clouds covering large portions of the sky. Formed by mixing of air masses. Low, thick, high albedo cooling effect. Nimbus, dark, shapeless, dense clouds. Exceptionally opaque to sunlight. Rain-bearing clouds. Precipitation. Definition: release of moisture when condensed particles grow too heavy for air resistance to hold against gravity. Types of precipitation. Hailstones, formed when water droplets are carried through alternating cold and warm layers by powerful updrafts, developing concentric layers. Graupel, soft hail, formed when supercooled water droplets freeze onto the surface of a falling snowflake. Snowflake covered by frozen droplets. Sleet, refrozen rain, small, clear ice pellets of frozen raindrops. Hits ground as solid ice. Virga, evaporating precipitation, raindrops that evaporate before reaching the ground. Drop size decreases with height. Types of rainfall formation. Convectional rainfall, common in equatorial regions and continental interiors. Heated land surface, warm moist air rises, convection cooling and condensation. Cumulonimbus cloud, short, heavy burst of rain with thunder. Orographic, relief, rainfall. Air ascends over a mountain on the windward side, adiabatic cooling and condensation, heavy precipitation on windward side. On leeward side, air descends and warms, adiabatically dry air, less cloud formation, rain shadow region. Cyclonic, frontal rainfall, convergence of contrasting air masses at a front. Warm air rises and cools, clouds form along front, prolonged, light. To moderate precipitation.
All right, Section 6, UPSC Prelims PYQs solved. We've built a really solid foundation today, so let's put it to the ultimate test and apply what we've just learned to solve some actual recent previous year exam questions. Let's do this.
Question 1, UPSC Prelims 2025. Consider the following statements. Statement I, the amount of dust particles in the atmosphere is more in subtropical and temperate areas than in equatorial and polar regions. Statement 2, subtropical and temperate areas have less dry winds. Which one of the following is correct? Option A, both I and 2 are correct, and 2 explains I. Option B, both I and 2 are correct but 2 does not explain I. Option C, statement I is correct but statement 2 is incorrect. Option D, statement I is not correct but statement 2 is correct. Pause 5 seconds. Answer, option C, statement I correct, statement 2 incorrect. Statement I true. Subtropical and temperate regions have dry winds, arid conditions, sparse vegetation, and stable high-pressure air, all of which generate and retain more dust. Equatorial regions have high humidity and rainfall that wash out dust. Polar regions have ice and snow that prevent dust generation. Statement 2 false. Subtropical and temperate areas actually have more dry winds, not less. That is precisely why they have more dust. Statement 2 is the opposite of the truth. Answer C. Question 2 UPSC Prelims 2025. With reference to the planet Earth, consider the following statements. I. Rainforests produce more oxygen than that produced by oceans. 2. Marine phytoplankton and photosynthetic bacteria produce about 50% of world's oxygen. 3. Well-oxygenated surface water contains several folds higher oxygen than that in atmospheric air. Which of the statements given above are correct? Option A, I and 2 only. Option B, 2 only. Option C, both I and 3. Option D, none of the above statements is correct. Answer, option B, 2 only. Statement I false. Oceans, through marine phytoplankton, produce more oxygen than rainforests. Statement 2 true. Marine phytoplankton and photosynthetic bacteria produce about 50% of world's oxygen. Statement 3 false. Well-oxygenated surface water contains far less oxygen than atmospheric air, not several folds higher. Atmospheric air has 21% oxygen. Even well-oxygenated water contains only about 8 to 10 milligrams per liter. Answer B. Question 3 UPSC Prelims 2024. With reference to water vapor, which of the following statements are correct? It is a gas, the amount of which decreases with altitude. Its percentage is maximum at the poles. Option A, 1 only. Option B, 2 only. Option C, both 1 and 2. Option D, neither 1 nor 2. Pause 5 seconds. Answer, option A, 1 only. Statement 1 true. Water vapor is concentrated in the lower atmosphere and decreases with altitude. Statement 2 false. Water vapor percentage is maximum at the warm, wet tropics up to 4% and minimum at the poles where cold air holds very little moisture. Answer A. Question 4 UPSC Prelims 2024. Consider the following statements. Statement I. Thickness of the troposphere at the equator is much greater as compared to poles. Statement 2. At the equator, heat is transported to great heights by strong convectional currents. Which one of the following is correct? Option A, both correct and 2 explains I. Option B, both correct but 2 does not explain I. Option C, I correct but 2 incorrect. Option D, I incorrect but 2 correct. Pause 5 seconds. Answer, option A, both correct and 2 explains I. Statement I true. Troposphere is 18 kilometers at equator and only 8 kilometers at poles. Statement 2 true. Strong convectional currents at the equator, due to intense heating, transport heat to great heights, pushing the tropopause higher. Statement 2 is exactly the correct explanation for statement I. Answer A. Question 5 UPSC Prelims 2019. Why are dewdrops not formed on a cloudy night? Option A. Clouds absorb the radiation released from the Earth's surface. Option B. Clouds reflect back the Earth's radiation. Option C. The Earth's surface would have low temperature on cloudy nights. Option D. Clouds deflect the blowing wind to ground level. Pause 5 seconds. Answer, option B. Clouds reflect back the Earth's radiation. On clear nights, Earth's surface loses heat through long-wave radiation. Surface cools, dew point reached, dew forms. On cloudy nights, clouds reflect back the Earth's outgoing radiation. Surface does not cool enough, dew point is not reached, dew does not form. Answer B. Question 6 UPSC Prelims 2019. In the context of which of the following do some scientists suggest the use of cirrus cloud thinning technique and the injection of sulfate aerosol into stratosphere? Option A. Creating artificial rains in some regions. Option B, reducing the frequency and intensity of tropical cyclones. Option C, reducing the adverse effects of solar wind on the Earth. Option D, reducing the global warming. Pause 5 seconds. Answer, Option D, reducing global warming. Both techniques are solar radiation management, SRM, methods of geoengineering to reduce global warming. Cirrus cloud thinning, thin high-altitude cirrus clouds trap outgoing long-wave radiation. Thinning them allows more heat to escape, reduces warming. Sulfate aerosol injection into stratosphere, reflects incoming solar radiation back to space, reduces insolation reaching Earth cooling effect. Answer D. Question 7, UPSC Prelims 2025. Consider the following statements. I. Without the atmosphere, temperature would be well below freezing point everywhere on Earth's surface. 2. Heat absorbed and trapped by the atmosphere maintains our planet's average temperature. 3. Atmosphere's gases, like carbon dioxide, are particularly good at absorbing and trapping radiation. Radiation. Which of the statements given above are correct? Option A, I and 3 only. Option B, I and 2 only. Option C, I, 2 and 3. Option D, 2 and 3 only. Pause 5 seconds. Answer, Option C, I, 2 and 3. Statement I true. Without atmosphere and its greenhouse effect, Earth's surface temperature would be around -18 degrees Celsius, well below freezing everywhere. Statement 2 true. Heat trapped by GHGs in atmosphere maintains Earth's average temperature at around +15 degrees Celsius. Statement 3 true. CO and other greenhouse gases are excellent absorbers of long-wave outgoing radiation. This is the greenhouse effect. Answer C. Question 8, UPSC Prelims 2025. The World Bank warned that India could become one of the first places where wet bulb temperatures routinely exceed 35 degrees Celsius. Which of the following statements best reflects the implication? I. Peninsular India will most likely suffer from flooding, tropical cyclones and droughts. 2. The survival of animals including humans will be affected as shading of their body heat through perspiration becomes difficult. Option A, I only. Option B, 2 only. Option C, both I and 2. Option D, neither I nor 2. Pause 5 seconds. Answer, Option B, 2 only. Statement I false. Wet bulb temperature of 35 degrees Celsius is specifically about the human body's inability to cool itself through sweating, not flooding or cyclones. Those are separate climate hazards. Statement 2 true. At 35 degrees Celsius wet bulb temperature, sweat cannot evaporate effectively because air is already saturated with moisture. Body cannot shed heat through perspiration. Core body temperature rises above 37 degrees Celsius, fatal even for healthy individuals. Answer B. Question 9, UPSC Prelims 2024. Consider the following statements. Statement I, the atmosphere is heated more by incoming solar radiation than by terrestrial radiation. Statement 2, carbon dioxide and other greenhouse gases in the atmosphere are good absorbers of long-wave radiation. Which one is correct? Option A, both correct and 2 explains I. Option B, both correct but 2 does not explain I. Option C, I correct but 2 incorrect. Option D, I incorrect but 2 correct. Pause 5 seconds. Answer, Option D, I incorrect but 2 correct. Statement I false. The atmosphere is heated more by outgoing long-wave terrestrial radiation from the ground, not by incoming short-wave solar radiation. The atmosphere is largely transparent to incoming solar radiation. Statement 2 true. CO and other GHGs are excellent absorbers of long-wave outgoing radiation. This is the fundamental principle of the greenhouse effect. Question 10, UPSC Prelims 2023. With reference to the Earth's atmosphere, which one of the following statements is correct? Option A, the total amount of insolation received at the equator is roughly about 10 times that received at the poles. Option B, infrared rays constitute roughly 2/3 of insolation. Option C, infrared waves are largely absorbed by water vapor that is concentrated in the lower atmosphere. Option D, infrared waves are a part of the visible spectrum of electromagnetic waves of solar radiation. Pause 5 seconds. Answer, Option C. Option A false. Equator receives approximately 5 times more insolation than poles, not 10 times. Option B, false. Infrared rays constitute roughly half, about 49% of insolation. Visible light is about 41% and UV is about 9%. 2/3 is incorrect. Option C, true. Infrared waves, long-wave radiation, are largely absorbed by water vapor concentrated in the lower atmosphere. This is why the lower atmosphere is heated. Option D, false. Infrared waves are not part. The visible spectrum. Visible spectrum is 0.4 to 0.7 micrometers. Infrared is beyond visible light at 0.7 to 1000 micrometers. Answer C. Question 11, UPSC Prelims 2022. Consider the following statements. High clouds primarily reflect solar radiation and cool the surface of the Earth. Low clouds have a high absorption of infrared radiation emanating from the Earth's surface and thus cause warming effect. Option A, 1 only. Option B, 2 only. Option C, both 1 and 2. Option D, neither 1 nor 2. Answer, option D, neither 1 nor 2. Statement 1, false. High clouds, cirrus, are thin and transmit incoming solar radiation. They actually trap outgoing infrared radiation causing a warming effect. It is low, thick clouds that reflect solar radiation and have a cooling effect. Statement 2, false. Low, thick clouds, stratus, have high albedo. They primarily reflect incoming solar radiation causing a cooling effect. They do absorb some infrared, but their dominant effect is cooling. Both statements have the effects reversed. Answer D. Question 12, UPSC Prelims 2025. Consider the following statements about January isothermal maps. Statement I, in January, in the northern hemisphere, the isotherms bend equatorward while crossing the land masses and poleward while crossing the oceans. Statement 2, in January, the air over the oceans is warmer than that over the land masses in the northern hemisphere. Option A, both correct and 2 explains I. Option B, both correct but 2 does not explain I. Option C, I correct but 2 incorrect. Option D, I not correct but 2 correct. Pause 8 seconds. Answer, option A, both correct and 2 explains I. Statement I, true. In January, winter in NH, land is colder than ocean. So isotherms dip equatorward over cold land and bend poleward over warmer oceans. Statement 2, true. In January, oceans retain heat, high specific heat, so ocean air is warmer than land air in NH. Statement 2 directly explains why isotherms behave as described in Statement I. Answer A. Question 13, UPSC Prelims 2024. Which of the following is our correct inference from isothermal maps in January? The isotherms deviate to the north over the ocean and to the south over the continent. The presence of cold ocean currents, Gulf Stream and North Atlantic drift make the North Atlantic Ocean colder and the isotherms bend towards the north. Option A, 1 only. Option B, 2 only. Option C, both 1 and 2. Option D, neither 1 nor 2. Pause 5 seconds. Answer, option A, 1 only. Statement 1, true. In January, ocean is warmer, isotherms deviate north, poleward over ocean. Land is colder, isotherms deviate south, equatorward over continent. Statement 2, false. Gulf Stream and North Atlantic drift are warm ocean currents, not cold. They make the North Atlantic warmer than expected, causing isotherms to bend poleward, northward, not southward. The statement says cold ocean currents, which is incorrect. Answer A. Question 14, UPSC Prelims 2023. Consider the following statements. Statement I, the temperature contrast between continents and oceans is greater during summer than in winter. Statement 2, the specific heat of water is more than that of land surface. Option A, both correct and 2 explains I. Option B, both correct but 2 is not the correct explanation for I. Option C, I correct but 2 incorrect. Option D, I incorrect but 2 correct. Pause 5 seconds. Answer, option D, I incorrect but 2 correct. Statement I, false. Temperature contrast between continents and oceans is greater during winter, not summer. In winter, land cools rapidly and becomes very cold while oceans retain heat, high contrast. In summer, both warm up, oceans also warm somewhat, lesser contrast. Statement 2, true. Specific heat of water is more than land. Water requires more energy to heat and cool. Question 15, UPSC Prelims 2024. With reference to Coriolis force, which of the following statements are correct? It increases with increase in wind velocity. It is maximum at the poles and is absent at the equator. Option A, 1 only. Option B, 2 only. Option C, both 1 and 2. Option D, neither 1 nor 2. Pause 5 seconds. Answer, option C, both 1 and 2. Statement 1 true. Coriolis force acts perpendicular to wind direction and its magnitude increases with higher wind velocity. Statement 2 true. Coriolis force is maximum at the poles and zero absent at the equator. This is why tropical cyclones cannot form at the equator, insufficient Coriolis force to initiate rotation. Answer C. Question 16, UPSC Prelims 2021. Consider the following statements. In the tropical zone, the western sections of the oceans are warmer than the eastern sections owing to the influence of trade winds. In the temperate zone, westerlies make the eastern sections of oceans warmer than the western sections. Option A, 1 only. Option B, 2 only. Option C, both 1 and 2. Option D, neither 1 nor 2. Pause 5 seconds. Answer, option C, both 1 and 2. Statement 1 true. Trade winds blow from east to west push warm surface water westward. Western tropical oceans are warmer than eastern sections. Statement 2 true. Westerlies blow from west to east push warm water eastward in temperate zones. Eastern sections of temperate oceans are warmer than western sections. Answer C. Question 17, UPSC Prelims 2015. Consider the following statements. The winds which blow between 30° N and 60° S latitudes throughout the year are known as westerlies. The moist air masses that cause winter rains in northwestern region of India are part of westerlies. Option A, 1 only. Option B, 2 only. Option C, both 1 and 2. Option D, neither 1 nor 2. Answer, option B, 2 only. Statement 1 false. Westerlies blow between 30° and 60° in both hemispheres, not between 30° N and 60° S specifically. That range mixes hemispheres incorrectly. Statement 2 true. Western disturbances, moist air masses originating from the Mediterranean, Caspian, and Black Sea regions travel eastward as part of the westerlies and bring winter rainfall to northwestern India. Answer B. Question 18, UPSC Prelims 2020. Consider the following statements. Jet streams occur in the northern hemisphere only. Only some cyclones develop an eye. The temperature inside the eye of a cyclone is nearly 10 degrees Celsius lesser than that of the surroundings. Which of the statements are correct? Option A, 1 only. Option B, 2 and 3 only. Option C, 2 only. Option D, 1 and 3 only. Pause 5 seconds. Answer, option C, 2 only. Statement 1 false. Jet streams occur in both hemispheres, not northern hemisphere only. Subtropical jet stream exists in southern hemisphere too. Statement 2 true. Only mature and intense tropical cyclones develop an eye, not all cyclones. Statement 3 false. The eye of a cyclone is actually warmer, not cooler, than the surrounding area. It is a zone of calm, warm, descending air. Answer C. Question 19, UPSC Prelims 2015. In the South Atlantic and Southeastern Pacific regions in tropical latitudes, cyclone does not originate. What is the reason? Option A, sea surface temperatures are low. Option B, intertropical convergence zone seldom occurs. Option C, Coriolis force is too weak. Option D, absence of land in those regions. Pause 5 seconds. Answer, option B, ITCZ seldom occurs. For tropical cyclone formation, a pre-existing low-pressure disturbance is needed. The ITCZ intertropical convergence zone provides this disturbance in most tropical oceans. However, in the South Atlantic and Southeastern Pacific, the ITCZ seldom rarely occurs, so tropical cyclones do not originate there. Question 20, UPSC Prelims 2013. During a thunderstorm, the thunder in the skies is produced by the meeting of cumulonimbus clouds in the sky. Lightning that separates the nimbus clouds. Violent upward movement of air and water particles. Option A, 1 only. Option B, 2 and 3. Option C, 1 and 3. Option D, none of the above produces the thunder. Answer, option D, none of the above produces the thunder. Thunder is not produced by clouds meeting, lightning separating clouds, or upward movement of air and water. Thunder is produced when a lightning flash superheats the surrounding air instantaneously to around 30,000 degrees Celsius. This causes the air to explosively expand outward as a shockwave. This shockwave is what we hear as thunder. None of the three options describes this correctly. Answer D. And that is a complete, in-depth walkthrough of Chapter 4 Atmosphere. We covered every single topic: composition, 5 atmospheric layers, insolation, albedo, heat budget, radiative forcing, wet bulb temperature, temperature distribution, isotherms, temperature inversion, pressure belts, atmospheric cells, all planetary winds, jet streams, polar vortex, local winds, air masses, fronts, tropical and temperate cyclones, extreme weather events, condensation, clouds, and all 3 types of rainfall. And we solved 20 previous year questions from 2013 to 2025. If this video helped you, please like, share, and subscribe. Drop a comment with which topic you found the most complex today. Stay consistent, stay concept driven, you will crack UPSC. Good luck.